Welcome to topics in knot theory, and we're on to what would probably be our last topic, which is a little bit about braids and variants of braids. So I hope to also tell you about a few variants of braids. But let's start with braids. A braid, or maybe I'll right away define Bn. So Bn is the nth, or you know what, maybe better, the braid group, the braid group on n strands, and as a set it's just the set of tangles on n strands. We already talked about tangles, but with the additional property that all the strands always go up. So I don't know, here is a 3-strand braid. Okay, sorry. Why isn't this? Okay, so here is a 3-strand braid. Okay? So the thing I am not allowing, just to be specific, so here is a non-3-strand braid. So here is a tangle in which you don't always go up. Okay, so here is a 2-strand tangle in which the first strand isn't always going up. So this is forbidden. And just names. So the number of strands is also called the width of the braid. So in our case it's n, or in our case it's 3. And a braid has a number of crossings, and the number of crossings is often called the length of the braid. Anyway, I said that braids make a group, and well, I should explain how it is a group. Sorry. So I should explain how it is a group, but maybe here is a better way. Instead of explaining how it is a group, I will tell you that it's obviously a group. So here is a braid. I don't know, let's make it a slightly different one. So you can intersect it with a 2-dimensional plane at height t over the basis. And let t over the beginning point, right? And let t rise. And when you intersect it with a plane t, you get n intersection points. And these n intersection points, since the strands are not allowed to touch each other, are distinct points. So any braid, so if you have a braid, it gives you can turn it into a map beta from, let's say, the unit interval. So let's say I parameterize it from the 0 to 1. So from the unit interval into the space of distinct n tuples of points. So this is the space Cn tilde, And let me explain what is Cn tilde. So let me first define Cn. So Cn will be the space of, well, maybe the easiest way to do it is to say that it's the space of n tuples z1 up to zn, all living in the complex numbers raised to the power n, but where you make the additional requirement that they're all different from each other. So if I is different from j, then zi is different from zj. Okay? Now, Cn tilde is Cn. Now, okay, the permutation groups on n elements, Sn, acts on Cn, obviously, by just permuting the coordinates. And Cn tilde is Cn divided by the action of the permutation group. And the reason I'm dividing by this action is because when you look at a braid, you get n points, but the points are not labeled. They're not labeled number 1, number 2, number 3. I don't have a particular, I mean, if I look at the whole braid, I can insist to number them by how they are numbered at the beginning point. But if I just look at a cross-section at time t, I have no specific reason to order them in any particular order. So hence, I regard a permutation of the points to be the same. Anyway, with this in mind, okay, so now suppose I'm allowing deformations of braids. That's the same as deforming the path beta. And so the conclusion is that Bn, and so the conclusion is that Bn is just the fundamental group of the space Cn tilde. In particular, it's a group. Okay? So the group is the multiplication in the fundamental group, but again, if you want to visualize it, multiplication in the fundamental group is concatenation of paths. So concatenation of paths would be, well, so a braid is like a path, and if you want to multiply B1 with B2, you just first do the first path and then the second path, which amounts to saying that you put the second braid on top of the first one. And the inverse is you go along a path backwards. So for braids it's the same. You just basically you reflect the braid on a horizontal plane. That's the inverse. Okay. Maybe if I'm speaking of a group, so I can also present it with generators and relations. So you can also view the braid group as the following. So it's clear that whenever you have a braid, you can decompose it into a series of crossings. So let me give names for these crossings. So let me declare that sigma k stands for the following braid. So it stands for, well, you have n vertical, you have k minus 1 vertical strands, then one strand or two strands that switch positions with a positive crossing in between them. So this is strand k and strand k plus 1. And then you complete it to n strands by adding additional straight lines. So clearly these generate. Whenever you have a braid, you can present it as a composition of such. And so Bn is the group generated by sigma 1 up to, well, you see, sigma k is a switching of strand k and k plus 1. So if I'm looking at n strands, I can only go up to sigma n minus 1. So it's generated by sigma 1 up to sigma n minus 1. And then subject to two relations. Okay? So what are the two relations? So the relations are basically inherited. Okay, the best way to view the relations is to view them as if they are inherited from knot theory, or not the best way, the easiest way given our current state of knowledge. Okay? Given what we already know, the best is to inherit it from knot theory. So I want to tell you what are Reidemeister 1, Reidemeister 2, and Reidemeister 3. So Reidemeister 1 has nothing to do with braids. Reidemeister 1 cannot be written in the world of braids. So nothing about it. Reidemeister 2 is really the relation, sorry, I wrote it wrong. So Reidemeister 2 is the relation that if you put a positive crossing and then a negative crossing, the product is 1. Okay? But I only gave you a generator for, right? I mean, sorry, this should be 1. So the product is, sorry, this should be equal to that, and this is what would be 1 in the, this is the identity braid. So, but I only gave you a name for the positive crossings. So by definition, by definition, the thing appearing here has to be the inverse of the thing appearing here. So that would be, so you know, if this is sigma k, then this will be sigma k inverse, because our product is the identity. And so I don't need to tell you what is Reidemeister 2. Reidemeister 2 is just the relation that a thing multiplied by its inverse is equal to 1. However, Reidemeister 3 does have a meaning. So if you draw Reidemeister 3, let me try to draw it. So, so this one goes like that. This one goes like that. Oops, sorry, no. This one goes like that, and the third one goes like that. So that's one side of Reidemeister 3, and the other side is, sorry about this little hook, I don't know, my screen is not perfect. And the other side of Reidemeister 3 is this. And if this is strand number k, and so if this is position k, this is position k plus 1, and this is position k plus 2, then the relation that you see here is, so maybe I'll start from the one on the right. So this is the relation sigma, so I switch k, I do a switch in position k, so this is sigma k plus 1, right? Then I switch in position k plus 1, and then again in position k. So sigma k is equal to, and here I start with a switch in position k plus 1, then in position k, then in position k plus 1. So is equal to sigma k plus 1, sigma k plus 1. And sorry, so maybe I was too optimistic about use of space. Sorry, let me right, so this is Reidemeister 3, But then there is yet another relation, which does not kind of correspond to a Reidemeister move. And the next relation is the relation that, so you see, in a group, the generators are always ordered. When we talked about knot theory, the relation that if you have if you had two crossings, you could switch their vertical order at no cost. So the equality, this is equal to that. Well, that was automatic. This was, we regarded the two sides of this equation as being the same diagram, right? But in terms of group theory, this would be sigma I, this would be sigma j, where I is different from j. And in fact, j should also be different from I plus 1. So this is sigma I, sigma j, and this would be sigma j, first sigma j, then sigma I. Okay? So there is an additional relation, and the additional relation is sigma I, sigma j is equal to sigma j, sigma I, provided I and j are not interacting, provided they're far away from each other, which really means if the absolute value of I minus j is greater than 1. This came too compressed, I'm sorry. Okay, now, if I were, strictly speaking, this requires a proof. Strictly speaking, I've asserted that pi 1 of a certain space has a certain presentation. The intuition should be clear. If I really wanted to prove it, I would have to spend some time with Van Kampen's theorem, but I don't really want to do it. I want to do other things, and it's the analog of the Reidemeister theorem, which I also skipped, so I feel comfortable skipping it. Okay? Anyway, why should we care? So we should care for two reasons, or several reasons, many reasons maybe. So one reason is that it's basically a place to play warm-up games. So it has features from knot theory, but it's a lot simpler than knot theory. So, you know, if we're lucky, I don't know how much time we will end up having, we will be able to prove things like, we don't know if finite type invariants separate knots, but we do know that they separate braids. Okay? We don't have a complete enumeration of finite type invariants for knots, but we do have a complete enumeration of finite type invariants for braids. So there are various places where you can play like games with braids and maybe learn a lesson about knots, okay? And in fact, there is something even sharper in this direction, namely, there is a map from braids to knots. So there is a map, there is a map from Bn, I'm not sure what to call this map. Maybe I'll call it A. Okay? And A here stands for Alexander, and in a minute you'll see why I call it A. So there is a map A from braids into actually knots and links. And the map is very simple. So if you have a braid, all you do is you so-called close it. So you connect the top to the bottom by closing it this way. Okay? So I closed it this way, but equally well I could take this bunch of strands and move it in front of the braid and then just close it sort of around this way, or push it further to the left and then close it on the left, or push it behind and close it behind. Okay? Maybe example. So consider the braid sigma 1 cubed, which is a braid inside the braid group on 2 strands, and let's compute what is its closure. So let's see what is the closure of this braid. So let me draw it. So here is sigma 1. Now let's do sigma 1 3 times. So 1, 2, I'm running out of space, so the third time I'll do it at the bottom. So here is sigma 1 cubed, and I can close it. I suppose I can close it this way. Equally well, I could have pulled one of the strands and closed it on the other side. So equally well, I could have closed it that way, but this is the trefoil knot. So this is the trefoil knot. And then comes Alexander's theorem, so which is why I chose the name A. So Alexander's theorem says that the map A is onto. In other words, every knot or every knot and link, so any knot or link is a closure of a braid. Not a unique braid. There are many braids whose closures are the same. Okay? But you can present every knot or link as a closure of a braid. So this means that you can study knots or links via braids sometimes if you also understand the kernel of the map. You can study knots and links in terms of braids, and people do it a lot. Okay? But let's get there, but let's first prove the theorem. So proof. So I'll do a schematic pictorial proof. So really I'm going to tell you, given a knot, how to go back to a braid, not a unique braid. Okay? So, so we're given a knot or a link. I don't know, maybe I'll call it L, because L is more general. It's link or knot. Okay? So it has crossings, I suppose. Some of them are pointing up, some of them might be pointing down, and maybe there are mixed ones. So maybe there is somewhere a crossing which is partially going up and partially going down. Okay? Also, it has strands, so it has pieces of wire going up, but somewhere else it might have a piece of wire going down. Okay? So basically the up ones are good and the down ones are evil, because in a braid everything will be pointing up. Okay? So I want to get rid of the evil parts. So part 1, the simplest bit is, well, if you have a crossing oriented the wrong way, well, we're in topology. I can just rotate it until it's oriented the right way. Okay? So, for example, let's take this one. So, if you have a crossing like this, I could rotate it by 90 degrees and it will become, oh my God, I'm always confused by these pictures. It will become this, and sorry, so if I start at the bottom left, I go here and then here. If I start at the bottom right, wait, I want to rotate it this way. If I start, what have I done? If I start at the bottom right, oh right, sorry, this connects to this. Sorry, I'm sorry, and this connects to that. Right, sorry. I don't know why I got confused. But anyway, if you look at the crossing now, it's a crossing in which both strands point up, but the price we paid was that we created more pieces of strand that go down. Okay? So similarly, maybe I will not risk myself doing it for this crossing, but it's clear that it can be done. Okay? So after you do this, you get a picture of the link in which all the crossings are good. So maybe I'll use green for good. So all the crossings are good. So they're all pointing up. And then you have pieces of strand in various places which are good. But unfortunately also pieces of strands which are bad. Okay? But you see, each piece of strand which is bad has, well, starts somewhere, so it's good until a point, and then continues somewhere, so then it becomes good. So basically I'm telling you, look at the pieces of strand from the point, so look at places where strands go down from the uppermost point to the lowermost point. So each piece of strand that's bad is like in between two segments that are good. Okay? So next, so I want to somehow improve the bad pieces. So I'll do the following. So suppose I have a note with, so suppose I have a link L. So here is my L, and it has several bad pieces of strands. There are no crossings on the bad pieces of strands because I've turned all the crossings so that they are pointing up. And of course each one is really sandwiched between better things. And then, you know, there may be more crossings and more strands around. Okay? So what I'll do is I'll pick a new color. Wait, and maybe I should be clearer. I mean, lines can go above, below. Okay? strands can go above and below the bad pieces of strand. Okay? So I'll pick another color, let's call it purple, and I'll connect all the top ends of the bad pieces to the top of the picture, going under anything that I see. And then likewise I'll connect all the I'll connect all the bottom ends of the bad pieces again to the bottom, going under everything we see, using purple lines. So again, I should have written it like it's it goes up right away. So I again connect it going under everything that it sees along the way. Okay? And then with the following provision, so with the additional provision, so I mean first, so what I do is, so the next step is I connect all, it's really, I'm connecting all the minima and maximas that appear in the picture. So all means to the bottom, and all maxes to top, with purple lines that run under everything, and with the additional provision that, so when I say they run under everything, I mean they run under the green lines, but with the additional provision that they never meet, so the purple and red lines never meet, and purples don't meet each other. So such that, and such that red and purple never cross. So the reds never crossed each other because all the crossings were pointing up. And the additional requirement is that the purples do not cross any of the reds. So this can be done because basically you have a bunch of intervals, and topologically there is no obstruction to connecting them to the bottom and to the top in a way that they will not intersect. I mean, there is no, basically, topologically the intervals are just points, or you know what? Maybe I'm saying too much. So, okay. Anyway, this done, you pull all the maxima and minima using Reidemeister 2's under all the strands that are on the way, until they're just at the bottom or just at the top. But so now red no longer, so now the red strands do cross other things because I create crossings. So maybe I'll show it schematically. So the next step is pull along purple, and the result will be, wait, maybe I should do it so that this is still visible. So the result will be, you will have possibly green stuff here, more green stuff here, you know, also green crossings. I don't interact with these ever again. Now the red stuff goes all the way from the top to the bottom, and the green stuff and the green stuff that connected to it that I pulled up goes like this. And the second one, I guess I dropped one of the three, so the second one again will go all the way like this, and the green stuff somehow continues from it. Okay? Is it clear what I've done? Okay? This is still the same knot. I've only done Reidemeister moves. Okay? But now we're done. Sorry?
Where are the pinks?
Pinks? The purple, you mean?
Yeah, purple, yeah.
Well, purple disappeared. I used purple to pull so I used the bottom purples to pull the minimas, and I used the upper purple to pull up the maximas. So I pulled them up and down, and now they disappeared. But I claim that I'm done, because now all the red strands are behind the picture, going from top to bottom. So basically the picture, if you redraw the picture on a cylinder, if you redraw the picture on a cylinder, you'll have, you can draw all the green stuff in the front, all the red stuff is going behind, so on the back side of the cylinder, and those points where green turns into red are just the points in which strands go from across the over of the cylinder, or across the top of the cylinder, from the top to the from the front to the back, and likewise on the other side. But this is a closed braids. This is just a, so now in front everything is green. Green means points up, and we close stuff in the back with an identity permutation, because the red things never cross each other. Okay, so this is a closed braid. So this is a closed, or the closure of a braid. In other words, the braid is the green stuff in the front of the cylinder, and the red stuff are the strands that close it. This is terrible. In my mind it was so clear and obvious, and somehow I completely failed to make it look clear and obvious. But I don't know. I hope it's at least passing. Okay. Well, are you okay? Is this acceptable? Okay, good. So the next theorem is Markovs theorem. So Markovs theorem. So, well, so every knot or link is in the image of a process, of this process. Okay? So you can ask yourself, when do two braids give the same knot and link, give the same answer? So the answer is the following. So if beta 1 and beta 2 are braids, then the closure of beta 1 is equal to the closure of beta 2 if and only if beta 1 and beta 2 differ. So roughly, there is some sort of Reidemeister moves. So differ by a sequence of moves as follows. So moves of the following, sorry, not as follows, but of the following kinds. Of the following kinds. So one, so just Reidemeister moves on braids. So clearly, right, if you have a braid and you perform a Reidemeister move inside it and then close, the resulting two knots are the same, or the resulting two knots are also differ by Reidemeister moves, which means that they are the same. Okay? Two, conjugation. So a braid beta gets replaced by gamma inverse beta gamma, where gamma is another braid. And this is also obvious. So if I have a, or it's one direction is obvious. It's obvious that this move does not change the resulting knot, right? So if you have a braid beta, or alternatively the braid beta composed with gamma inverse and with gamma, and if you close beta, let me stop at 3 strands, and you know, maybe I'm being too careless. So let's just make them 3-strand braids to start with. So if you close beta, or if you close gamma inverse beta gamma, so if you close the thing on the right, well, you can slide gamma around the bend. So once you got a link, you can slide gamma around the bend, and then it cancels this gamma inverse, so these two are equal as links. Okay? And then the last property is the following. So if beta is a braid in the nth braid group, then beta is equivalent to beta multiplied by sigma n to the plus minus 1, where I remind you that sigma n is the braiding of strand number n, the braiding in position n. So it's the braiding of the m position with the n plus first position. So this actually lives in Bn plus 1. Okay? So all the previous relations happened within a single braid group, but this relates a braid in Bn with a braid in Bn plus 1. Anyway, why is this relation true? So, or why is it true that this relation is in the kernel of A? So, if this is the braid beta, so let's say n is equal to 3, and now I multiply by sigma n, so sigma n goes one step beyond, and now, so really I'm multiplying by, so I'm adding one strand, so to be precise, I'm adding one strand to beta and then multiply by sigma n. So, so now I added this extra strand with an extra twist, and now suppose I close, so this connects to this connects to that. Let me be lazy and close the other two on the other side, basically for space considerations. But the point is that I can now undo this kink and with a Reidemeister 1, and I just got the closure of beta. Okay? Okay, so what I've shown you is that the three relations are in the kernel of A. So if two braids are related by any one of these three relations, then their closures are the same. The hard part is the other direction, right? So the easy part I've shown, but it's harder to show that if A of beta 1 is equal to A of beta 2, then beta 1 is equivalent to beta 2 modulo these relations. Okay? It's actually not so hard, and I'm debating whether it's an appropriate homework assignment or not. But anyway, let me give you a hint. So basically, all you have to do is to really understand the process I've written here. So all you have to do is to say to yourself, suppose I start from two knots that are, well, suppose I start suppose I start from two knot diagrams that represent the same knot. What kind of two braids, or how do the two braids that I'll get out of them relate to each other? So the problem is that there are several choices within this process. So first of all, I had to choose whether to spin the crossings to the left or to the right. Okay? So so you choose between, so suppose you've chosen to spin left, and now you spin them to the right. You have to see how this affects the end result, and all you have to do is to check that it affects the end result by one of those Markov moves. Okay? Likewise, so I told you choose purple line. Purple lines going, telling you how to pull the minimals and maximals to the bottom, to the bottom and to the top. If you had chosen different purple lines, what would happen? But you know, the choices, there is a limited freedom in how much to choose the purple line. Basically, you can move them left and right past other features. Okay? So, again, how will this affect the end result? And finally, suppose the two braid diagrams to start with differed by Reidemeister moves here. How will this affect, the two knot link diagrams we started with different by Reidemeister moves here, how will this affect the end result? So, I mean, there is a lot of labor here, but nothing that's fundamentally difficult. Okay? So, I'll go 1 minute further. So, basically, the conclusion is, if you wanted to construct knot invariants, one of the ways to do it would be to construct braid invariants that are invariant also under these moves. Okay? And we'll talk about it next time. Sorry, I don't know. Okay, you know what? Let me first of all quit the video.